Okay, so we're live on YouTube. Okay, and I guess I will let the participants in already little by little in case they have things to ask. Okay, I will go ahead. Good morning, everyone. If you're joining us now, welcome. So we will wait for more attendees to join before we start. Meanwhile, if you have any questions, you can post them in the Q&A if it's material related, or chat if it is just some logistics questions. But we will send you a reminder of all the links just in a minute. Good morning, everyone. We're still waiting on roughly half of the participants to join, so we will give it a few more minutes before we start. Okay, good morning once again. So I think we have enough people joining us in now so that we can go ahead and get started. So I hope you're doing well. I hope that the program yesterday was useful for you and you were able to revisit it and go over some of the details to be ready for today. So just some kind of logistics announcements before we start with today's program. So we did post the live stream video of yesterday's program on the YouTube channel. So let me post right now in the chat once again if you missed that information. So I'm just posting in the chat for everybody else. These are the YouTube videos. Okay, so you have the link right now in the chat. It's the same link as before. So this is the video from the main webinar yesterday. So the advanced group, we're still working on that video. So we hope that we will be able to post it a bit later. So we did not forget about that. So the second link that may be relevant is the GitHub. Again, same link as yesterday. No changes. So this is the GitHub with all the materials specifically for today. If you scroll at the very bottom of the GitHub, so there's lecture slides for today and also for yesterday. So you will be able to see it. And Kylie just posted the Dropbox, but the material on Dropbox is the same as on GitHub. So this is just being redundant. So on the GitHub, we now have the solutions of the exercises from yesterday. So I hope that this can be useful for you as well. And today we have the same plan as far as logistics as yesterday, in the sense that we will have a combination of lectures and a combination of hands-on practices with teaching assistants. I just want to clarify one of the questions that came up yesterday, why we're not using breakout rooms from the webinar, but why we're using separate Zoom links. So the reason for that is the breakout rooms, well, first of all, it would require different infrastructure, but also they would force us all to come back at the same time. But what we want to do instead is to give you time, the opportunity to spend more time with teaching assistants, especially if you fall behind, or if the main room is too slow and you feel like you would like to spend more time going faster, in which case you can just work with your teaching assistants on your own time. So today we will have, as yesterday, a combination of lectures and TA, but we really encourage you, if you would like, stay in the TA room more time, ask them questions if necessary. You can monitor on YouTube what's going on in the main webinar. So if the speed in the main webinar is good, do that. If it's too slow or too fast, just stay back at the separate link with your TAs and get answers to your personal questions so that you get as personalized help as you can. So for today, so make sure you check again the email. So the email from last Thursday, the title was ASMS Fall Workshop, Logistics and Login Instructions. So you will have, some of you will have different TAs for the second day. So when it's time for you to go to your breakout rooms, please go to TAs, to the link that corresponds to November 8th. So this is the right link for today. Again, the title of the email, and I will just put it in the chat for you. This is the ASMS fall workshop, so you will find. And this email was from November 5th, from last Thursday. So this is all I have to say as far as logistics. If you have more logistics questions, please put them in the chat window. Otherwise, all the questions regarding the actual presentation are, it is best for us to handle them in the Q&A window, because then we can triage them a little bit easier. Okay, so without further ado, let me introduce once again our instructor today, Kylie Bemis. So Kylie is a faculty at Northeastern University, and Kylie made important contributions in developing our packages for mass spectrometry. Kylie is also an instructor in our data science program at Northeastern University. So we are very fortunate that Kylie could take the time with us today and talk about data visualization with Ggplot. Thank you very much, Kylie.
Thank you, Olga. Hello, everyone. So as Olga said, I'm Kylie Bemis. I'm an instructor in the Masters for Data Science program at Corey College for Computer Sciences at Northeastern University. And I've also worked quite a lot with R. I have two packages on Bioconductor for working with mass spectrometry imaging data, and also for working with larger than memory data. So file-based data. I work a lot with Ggplot too in terms of teaching it in my classes, and so I hope that today's material is useful for you. So we'll have kind of two main sections of the material we'll be going through today. All of the material is available on GitHub and Dropbox. So let me quickly switch over to my browser. So here, if you have the GitHub link, which Olga posted in chat a moment ago, if you go through to exercises and then day 2, you can find the R code that I'll be working from. These are in RMarkdown documents. I don't know if Ryan had a chance to explain RMarkdown yesterday. I know Mina will teach much more about RMarkdown and reproducible research next weekend on Saturday. So if you're not familiar, these are just documents that have a combination of text and embedded R code. So on GitHub is just the R Markdown source code. So this includes the actual R code. And if you just want access to everything from today's material, so that includes both the R code, the HTML documents that I'll show you in a moment, as well as the slides that I'll be going through at the beginning. You can download that from this Dropbox link. This has also been posted in chat, as well as being available here on GitHub from this link on GitHub. So that is where you can find the material. In terms of working through the R code today, I'll be working from the RStudio Cloud instance for day 2. So you should find a day 2 data visualization with Ggplot 2 on RStudio Cloud. If you want to work from your own local RStudio app, that is fine too. You may just need to download and install some additional packages that have been already installed on RStudio Cloud, as well as make sure that you have access to the data sets. I'm using primarily the same data set from yesterday, the IPRG data set, but there's a few other data sets that I'm also using as well that are more useful for showing some different material.
Kylie, there's a question which may be good to answer live. How do people open the RMD file in case they want to look at that?
So if you download from the Dropbox link and have, let me switch over to Finder window. So here, if you have, so this is all of the material that's included in the Dropbox link. So you have the slides, some HTML documents, as well as the RMarkdown documents. And if you have RStudio installed locally, just double clicking on this will open RStudio. These are also available on the RStudio Cloud instance. So if I open this locally, it will open in RStudio and look like this. So this is my local RStudio application. So you should see something like this. You can also just, if for some reason it doesn't open in RStudio automatically, if you open RStudio, you can open it through there. But these exercises, these RMD documents are also available in the RStudio Cloud instance that I'll be loading up in a moment. So you can access these through the RStudio Cloud instance as well. So I'm going to go ahead and close that. Go back to my browser. So I'm going to go ahead and open my version of the RStudio Cloud. And so this is where I've also included all of the RMarkdown documents for today. So you will be able to open those directly through RStudio Cloud. And the data sets that I'll be using will also be there. So if you were to open one of the HTML documents that is available in the Dropbox link, you should see something like this. And these are the same material as in the RMarkdown documents, just kind of exported into a version for display or for presenting to other people. So as Mina will discuss more next weekend, RMarkdown is a way of preparing a document that includes both our source code as well as markup, figures, text, and combining all of these together into a single document or report. And so in RStudio Cloud, so I have RStudio Cloud open now. This is my personal instance for day 2 data visualization. I'm going to open the day 2a, ggplot2.rmd. And this shows the RMarkdown document. So you can see that there is some R code in combination with some plain text. And there is also an HTML version of this that is the same material, but exported to an HTML version. And so there's 2 main RMarkdown documents that I'll be going through that show the code that I'll be working through today after I've gone through the slides. So there's a day 2a, that is the first set of code that I'll be going through and working through with you together that discusses or demonstrates ggplot2 and how to create a lot of basic data visualization using the ggplot2 package. And then there's a day 2b, RMarkdown as well as HTML, and these will go through in kind of the second half of our session, and these show some more kind of advanced analysis that you might be doing specifically for mass spectrometry data, showing things like some clustering or heat maps, that kind of thing. So a little bit more specialized plots that are a little bit more advanced that we'll talk about in our second half. And then as well, I have a day 2 exercises. So unlike yesterday, the exercises that I'm giving you today actually have the solutions already embedded in them. If you open the RMarkdown version and you don't want to see the solutions yet, instead of the RMarkdown version, just open the HTML version. So in the HTML version of these exercises that I have for you, you should see just the text asking you what to do for the exercise. And then there should be a little button to expand the code that will give you the solution. So I encourage you to open the HTML version of these exercises. Try to work through the questions yourself when we get to that point in our session. And then once you think you have a solution, or as you're working with your TAs in our Zoom help rooms, once you think you've gotten to a solution or you want to see the solution, then you can click the code button to expand and see the code for the solution. So you already have both the questions as well as the solutions, which in the HTML version are currently hidden. So that's the basic setup for all the material that I'll be going through today. And so now I will go back to the slides and we'll go ahead and get started. So at the beginning here, I'm just going to go through some slides that will set up kind of the basis for how the Ggplot2 package works, because it's built on this system called the grammar of graphics, which is a little bit of a different way of approaching data visualization than you might be familiar with. So this is my only set of slides for today. I'm just going to go through these at the beginning, and then after we get through this set of slides, the rest of the day I'll be spending in between the HTML documents and my RStudio Cloud instance, working through some example code with you, showing you how to do all of this. And then once we get to certain points, I'll let you go off and work on some of those exercises. So for now, we'll go ahead and get started with the slides. So we'll be talking about data visualization. I'll start off with just kind of the basic idea of why it's important to look at data in the first place. I'm sure this might be a basic question, but it's important to consider why we actually want to look at our data after we think of doing data analysis and using R. We get all of these statistical results. So we have things like p-values. We've done things like build linear models that you'll hear more about all of that later on next weekend. Performing statistical analysis in R. So we have these advanced statistical results, but it's still important to just perform the basic step of actually looking at our data and performing data visualization, even when we have all of this advanced statistical machinery. So as an example, here is a data set that looks like a dinosaur. So I've made a simple scatter plot of this data set. So this is a data set with two variables, x and y. And if we plot these two variables, x and y, against each other in a basic scatter plot, we can see it looks a lot like a T-Rex, a lot like a dinosaur. And this actually comes from a set of 13 different data sets. So this is the first data set in this set. And if we look at the statistical summaries of this data set, well, we have a particular mean for both the x and y variables, a particular standard deviation for both the x and y variables, and a particular correlation for the x and y variables. And so if we set up, if we just look at the statistical summaries, there's actually, we actually have 13 different data sets. I'm not showing you the other 12 data sets, but what I am telling you is that all of these 13 data sets have the exact same statistical summary. So all of the 13, we have 13 data sets that have the exact same mean for the x variable, the exact same mean for the y variable, and the exact same standard deviation for both x and y, and the same correlation between x and y, 0.06. If we look at the correlation, 0.06, and you're familiar with correlation, this measures kind of whether if there's measures the strength of a linear relationship between two continuous variables. Closer to 1 means that there's a very strong relationship. Closer to 0 means there isn't. Whether it's positive or negative measures the direction of the relationship. So here, correlation being close to 0 would suggest that there's not much of a relationship between x and y. But of course, if we look at this scatter plot, we see that there is a very strong structure to x and y. We can see it looks like a dinosaur. So correlation on its own doesn't tell us too much in this case. And if we look at the statistics, well, we have 13 data sets with the same statistics. But now I'm going to go ahead and show you what these other data sets actually look like. So here are data sets 2 through 13. And if we were to just look at the statistical summaries, these will look very similar because they share the same means for x and y, the same standard deviations, and the same correlation. But when I actually go to visualize them and create scatter plots between the x and y variables for these other 12 data sets, I find some really unique patterns, and they all look very different from each other. And not only that, but I can see the correlation doesn't necessarily tell me much because I can see that there is some very strong structure and relationships between x and y in all of these data sets. But the most important thing being that these are very different data sets. And so just looking at the statistical summaries on their own doesn't actually tell us much. And so the set of data sets is called the Datasaurus dozen. It just goes to show that it's important to look at data to visualize data because just looking at statistical summaries is often not enough. So we know that looking at data is important. Summary statistics don't tell us the whole story. Looking at data makes it easy for us as humans to find patterns, do things like identify potential outliers that it can be difficult to measure just through statistics. When we go and actually do some sort of fitting of a statistical model, which you'll learn more about next weekend, it's important to check model assumptions. Visualization is great for that. And even after you actually have your analytic results, whether those are statistical tests and p-values for those, or some other kind of clustering or machine learning method, visualization is still important to actually intuitively display the results of that statistical analysis. The figure is always going to make things a little bit easier to understand. So we know that data visualization is important. So now maybe you take a moment to just think of what are some of the common ways that you look at data. So just take a moment, give you a couple seconds, and think in your own mind, what are some of the common statistical graphics that you might use to actually look at data? All right, so some of the things that you might have in mind in terms of ways that we look at data using statistical graphics are things like scatter plots, line plots, box and whisker plots, or more commonly just called box plots, are really good. Histograms can show us the distribution of variables, or bar plots can give us an idea of counts of variables. So these are some common statistical graphics that I'm sure most of you are at least somewhat familiar with. So scatter plots, looking at two continuous variables. Box plots, very useful to compare the distribution of variables across different levels of a categorical variable. All of these are very common statistical graphics. And each of these different graphics often has a particular role that it performs in terms of why and when we use it for visualization. So some of these graphics are more just for looking at a single variable, and some of these graphics are let us look at 2 or more variables. So for example, histogram gives us an idea of a distribution for one continuous variable. Bar plots also show us the distribution of a single categorical variable. Pie charts as well, we won't really be talking about those. Whereas other statistical graphics like scatter plots help us look at the relationship between 2 variables. Same thing with line plots. Box plots are very nice because they can both serve as a way to visualize the distribution of a single variable, but also can be used to let us compare the distribution of a variable across different levels of a categorical variable. And something else we'll talk about that you may or may not have heard about before is called faceting. And faceting is a technique that lets us break up a single large plot into smaller subplots that give us a better idea of different subsets of our data. And this is another way that we can look at 2 or more variables. Some other ways that these different visualizations have different roles is some of these lets us look more at the distribution of variables. So histograms, bar plots gives us an idea of distributions, whereas others like scatter plots are more designed to let us see relationships between variables. So this is all going to kind of lead us into how the Ggplot 2 package kind of has a unique way of letting us work with data visualization and these different kinds of statistical graphics that we commonly use. So my question now is, how do we actually go about plotting data? If you wanted to create, say, a scatter plot or a box plot or a histogram, things like this, you might think that the easiest way to do this would just be to use the name of the graphic that we have. So, and this is actually the approach that Base R takes, as well as lots of other graphical packages. So we might have a single function, maybe call it plot, that takes care of creating scatter plots, because those are pretty common. We might have another specific function that just does box plots, and we can call that box plot. So this function just does box plots, that's what it does. And we might have another function that just does histograms, and this is what that function does. So this is one possible approach that we could go to graphing data and plotting these kinds of statistical graphics, is just have one specialized function, and all it does is it specializes in plotting that particular kind of graphic. But there might be a better way to kind of approach this. And so as we think about these different kinds of graphics, scatter plots, line plots, box plots, and think about kind of what they have in common between them. And if we can kind of break down these different ways of visualizing data into a common language, a common list of ingredients that goes into building any kind of statistical graphic from scratch. So take a moment, try to think what are kind of the common things that all of these different graphics share in common. So some things that you might have thought. So most of these map variables to X and Y axes. So scatter plot, line plot, both of these map variables specifically to position. The X and Y axis is used to represent, the position is used to represent values of continuous variables. Box plot also maps things to X and Y axes. Same with histograms and bar plots. So we use position to map the values of variables. We use some kind of mark or geometric object. So scatter plot uses points to represent observations. Line plot uses lines. A box plot uses a slightly more complex geometric object, a box with whiskers on it, to show a 5-number summary in addition to outliers. Histograms and bar plots both use bars and the length of the bars to represent things. So all in all, we have things like position. We have things like different geometric objects or marks that we use to draw on the canvas to represent things. So the key ingredients for statistical graphics that we can use are firstly some kind of data. So we always start with some kind of data, right? We have a data set that we want to visualize. We have some way that we encode that data into different aspects of the plot. So we use some kind of marks or geometric objects. So these are things like points, lines, the actual things that we draw on a canvas to represent our data. These are the geometric objects. And we have different channels or aesthetics of the plot that we use to encode the values of our data. So these include things like position along the X and Y axis, or the color or size of points. So these geometric objects and aesthetics or marks and channels are the way that we encode our data into the different aspects of a plot. We might have things like statistical transformations. So in the case of a box plot, we need to transform the data from all of the individual data points into some sort of 5-number summary. Same thing with a histogram. We take all of our data and bin it into particular bins so we can plot the heights, the counts of those different bins. We have some kind of coordinate system, usually a Cartesian coordinate system with an X and Y axis. But we could also have different coordinate systems. So for example, we could use polar coordinates to draw a pie chart or something like that. And we also have some kind of scales and annotations. So we have the axes themselves. We have labels for our X and Y axes, a title, and a legend. So all of these are the different key ingredients for plotting these statistical graphics. So let's consider a very simple data set. So we have 4 variables, A, B, C, and D. With these values, A, B, and C are numeric. D is a categorical variable, so it takes values A and B. This is an example from a paper by Hadley Wickham, who is the author of the Ggplot 2 package. So this is from a paper that he wrote explaining this concept of a layered grammar of graphics and building up a plot from these different key ingredients. So what we want to do is create a scatter plot of A versus C. And maybe we want to include D in that plot somehow as well. So the way that we go about actually doing that is we map the x-axis position along the x-axis to A. We map position along the y-axis to C. And we can map some other aspect of the plot, so maybe the shape of the points, to D. So now, after doing that aesthetic mapping, we now have X, Y, and shape from A, C, and D. So this is the aesthetic mapping of the plot, or how we're going to actually encode the data onto our canvas, onto our plotting canvas. So we have some kind of marks or geometric objects. So these are the actual points that we're going to use to draw on our canvas. We have some kind of scales and a coordinate system. So we have our axis labels and the axes themselves, and plot annotations. So we have things like the title and axis labels and so forth. And we put all of these together, we have a plot. We can do a more complex plot. So for example, we can facet. So this is one of those concepts I mentioned. So we can, faceting, what this does, faceting splits the data into different subsets, usually based on the levels of some categorical variables. So in this case, based on D. We're splitting the data into subsets. So here D equals A, I think, and then D equals B. And we're going to create subplots for each of the different subsets of data. And the important part of faceting is each of these different subplots will share the same scales, the same axes. So that makes it really easy to compare between the different subplots and find out if there is some kind of change in the relationship, say between A and C, depending on D. So faceting is really useful for that kind of thing. So now we can kind of build up a vocabulary for how to create plots based on these different key ingredients that we've identified. So some more advanced things that we can do is we can have different layers if we want to overlay plots on top of each other. So say maybe we want to have a scatter plot, but on top of that scatter plot, we also want to have some kind of smooth trend line or a regression line or something like that. We could plot multiple data on the same plot. So we could have multiple data sets on the same plot. We want to apply some sort of statistical transformations, so binning or 5-number summaries for box plots, for example. We might want to apply some sort of position adjustment. So we haven't really talked much about this, but say you have a bunch of data points and they're all rounded values and they're plotted directly on top of each other. We might want to add some kind of jitter to break those points up a little bit. And we want some way to build up plots programmatically from this list of key ingredients that we have. And so this is where Ggplot2 comes in with this idea of this layered grammar of graphics. So every plot in Ggplot2 is built up of all of these different components. We have some sort of default data set. We have some sort of default set of aesthetic mappings between variables and different graphical aesthetics. So that sounds complicated, but all that really means is we are mapping variables to different aspects of our plot, such as the X and Y axis, shape, color. That's the aesthetic mappings that we're going to use. Then we have one or more layers of our plot, and each of these layers can include some kind of geometric object that we're actually going to draw on the canvas, some kind of statistical transformation. If in the case of no transformation, we would just call that the identity because we're just returning the same data. But we might have some sort of statistical transformation or position adjustment if we need. Optionally, each of these layers could also include a new data set or its own set of aesthetic mappings. And then finally, we need a scale for each mapped aesthetic. So what the scale is if we're having, say, color represent values of a particular variable, the scale says which color represents which value. Or if we're using shape to represent values, then which shape represents which value. So often the scale is what will show up in our legends. And then some kind of facet specification. So we might have no faceting, but we might also want to facet by some variables. So we have we want to have visual encodings. Those are marks. So these are the actual geometric objects we use to draw a graphic. We can choose things like points, lines, areas, different polygons. We could use, there are other kinds of things that we could use here. So containment, so especially if you do some kind of clustering, you might want to show those different clusters in terms of containment. So you're not using a line to draw to contain those clusters. If you have some kind of network, maybe you're trying to show interactions between proteins or something like that, you could show a graph and the links could be the geometric object that you use to show that. So we have these different marks or geometric objects that we use to draw the graphic. And then different channels are what we use to actually encode the values. So these are the aesthetics and scales that correspond to them. So color, value, texture, symbols. These are all the different channels that we can choose from to display values in different ways. So we have color. We can also use value or saturation. We can use size and the scale of a point or of shapes. Orientation is another thing we can use. Length is a really strong way to encode values. Symbols, so the shapes of the points as well. So these marks and channels or geometric objects and aesthetics, all of these come together to really define what the actual plot is, what the statistical graphic is that we're using. So your choice of the geometric object and the aesthetic mappings, as well as the scales. So which color represent what value, what shape represents what value. The choice of geometric object, aesthetic mappings, and scales define the actual statistical graphic. And the point of Ggplot2 is we specify our plots in terms of these geometric objects, aesthetic mappings, and scales, rather than just having a single function that is dedicated to creating a specific kind of plot. In addition, we have some kind of statistical summaries. So if we wanted to create a box plot, we need a language for being able to define. We want to statistically summarize our data into a 5-number summary. For histogram and bar plots, we also have a transformation in either binning or counting. We might have position adjustments as well. So say we want to create a bar plot and use, for example, the fill color of the bars to represent some variable. Then the position adjustment is what defines how we arrange those different bars. So we could have them side by side, or we could have them stacked on top of each other. And we can also specify different coordinate systems. So most often we'll have Cartesian coordinate systems, but we could also have things like polar coordinates, or probably no need for maps in mass spectrometry, but we could also have a map coordinate system if we were plotting, say, maps. If you're watching, say, election coverage in the past few days, you probably saw a lot of graphics that used mapping coordinate systems. So the idea behind all of this is that we have a package, Ggplot2, that fully implements this idea of a layered grammar of graphics. And so rather having a single function that is dedicated to creating, say, a scatter plot or a histogram, instead we have multi-purpose functions, and we can specify the default data set, we can specify our aesthetic mappings, and we can specify the geometric object. And this combination of choices is what creates the graphic for us. So this is an example of kind of a template for the way that we would specify all of these using Ggplot2. And it looks kind of complicated at first, but usually because we have a lot of defaults, so we have, there's a lot of things that we can usually assume. So usually we're going to want a Cartesian coordinate system. So we don't usually need to specify the coordinate system that we're going to use unless we're using something different. So in most cases, what looks like a kind of a complex system of all of these different choices, usually we can have a much simpler way of expressing these. So usually we just have to specify the data set, the aesthetic mappings, and then some kind of geometric object or geom function, as we'll call them, that defines what kind of plot we're using. All right, so now I'm going to go ahead and go over to my RStudio Cloud instance and walk you through how to do some of this in Ggplot2. As a reminder, there is a Q&A open if you want to ask a question regarding the content specifically. I'm going to also check right now, so I'm going to launch a poll real quick to see how the presentation speed is for everyone so far. All right, so it looks like things are going fine so far. So we'll see, I'll check in again when we work through some of the R code to see if everything is continuing to proceed well. All right, so I'm going to go in my RStudio Cloud. I'm going to quickly rearrange my, oh, looks like it might need to reload. I guess I left it alone for too long. try refresh. Let's reload this. Okay, that is very strange. All right, there we go. I'm not sure what was going on with that originally. So I'm going to quickly rearrange my panels just a little bit so I think it's easier to see the code. And I'm also going to change this. So you're going to see where I'm going. If you want to set up yours in the same way, you don't have to. I'm going to Tools, Global Options. Under pane layout, I'm just moving my console to be on the right here so I can have a little more room to display the code on the left-hand side here. And I'm also going to go to RMarkdown here, and I'm going to uncheck this option to show output inline for Markdown documents. So what this does is usually if I had this checked when I go to run code in my R Markdown document. So this is just basically an R script that has text and figures in it and can be exported to a more display report format. If this were checked when I go to run code, it would show up inside of the document here rather than on the appropriate panels in RStudio. I'm going to uncheck this so that everything shows up in the way that it normally would if this were just a regular R script. So I'm unchecking this show output inline for our Markdown documents. All right, so if you open your own instance of Day 2 data visualization with Ggplot 2, you should have access to all of the material here. I'm currently in Day 2A, ggplot2.rmd. If you want to follow along just with the material, but not necessarily run these yourself, you can just open the HTML version. That looks like this. So this will show you all of the code and the output and the figures in a kind of a report format. So you can follow along with that if you don't want to run these yourself right now. If you want to run the code along with me, or after we take a break to go to TAs, then you can open the RMarkdown version and run these with me. So a quick lesson in RMarkdown is that you have these different code snippets or code chunks. So surrounded by these triple backticks are the sections that have the R code in them. And outside of these code snippets are just different text or markup that will affect the formatting in the document. The way that I created these HTML documents is I click the knit button here. And that compiles all of this together, runs all of the R code, and outputs it to, in this case, an HTML document. You could also output to PDF or other formats like a Word document and so forth. I have outputted them to HTML, and Mina will tell you more about how to use and prepare your own R Markdown documents next weekend. For now, I'm just going to show you RStudio formats these nicely. So there's a little run current chunk button that lets you run all of the code in a particular chunk. So this is a common error that some people have been getting when trying to load the tidyverse in RStudio. I've gotten this a lot lately, and I'm not sure why. What has been working for me, if you get this same error, is just go to Session, restart R, and hopefully now it will work. I'm not sure why. Lots of times the first time I run this and try to load RStudio, for some reason I get this error. I'm not sure where this is coming from, but just restarting R from within RStudio without restarting RStudio itself. You can just restart the R instance through session here. And that seems to kind of reset things and allow me to load RStudio. Again, I'm not sure what the source of that problem is, but it seems that restarting R fixes it. All right, so I've loaded the tidyverse. So this is the collection of packages you were working with yesterday. It includes things like dplyr, as well as the Ggplot2 visualization package we'll be using today. And the first thing here is this data set, this data source dozen data set that I showed you initially. I'm not going to go through this because this is just creating the same plots that I showed you at the beginning. And you can see here I'm using some dplyr code as well as some Ggplot code. I'm not going to go through these right now. But if you want, after we've done everything for today, something that might be good is to go back and look at these code chunks for what I'm doing up here and try to understand exactly what's going on. But these were just to create the figures that I showed you earlier. OK, so the example data that we'll be working with, the first one that I'll be using is the IPRG dataset, the same dataset that was used yesterday. So there's a question: to work with offline RStudio, do tidy packages have to be installed to start with? So if you're using your own version of RStudio, your local an RStudio app, you do need to make sure to install the tidyverse as well as the other packages I'll be using. So I will be using some other packages as well. I think when you first load up when you first open the RMarkdown document, RStudio often has a little reminder that there are some packages that this document uses that are not installed yet, and it'll give you the option to install all of them at once. If not, for any packages that are on CRAN, like the tidyverse, you just need to install those using install.packages. For some of the other packages that I'll be using, the ones that are on Bioconductor, you need to install those through the BioCManager package. So you need to first install the BioCManager package and then install, say, the MSStats package. So you would do that like this. So you do need to make sure that you have all of the packages installed yourself if you are using your own local RStudio app. I'm not going to go through that right now in any more detail than that, since I'll be working from the RStudio Cloud version. So usually restarting there's a question if it takes a long time to restart the R session. I'm not sure how long it usually does not take very long. The first time you load up the RStudio Cloud instance, that will take a while. But if you just go through the restart R here, that should not take very long. If it does, I'm not sure why it's taking especially long. It might be because there's many of us using this. But I'm not sure exactly why. It does not usually take very long just to restart the R. Restarting the whole RStudio instance would take a while. But if you're just restarting the R kernel, what we call it, the R kernel, so the actual underlying RStudio is R itself. I think Ryan went through the differences between R, RStudio, and RStudio Cloud. If you're just restarting R and not RStudio itself, it should not take long. If it does, that's a little bit not normal. Hopefully, it would not take very long in the future. All right, so I'm going to use this IPRG dataset that was used yesterday. In order to get to the version of it that I'll be using, some pre-processing needs to be done. I'm not actually going to go through this pre-processing. If you're using RStudio locally, you can feel free to go through this. But you also have, if you're using RStudio Cloud, you should already have the processed data that I'm about to use. And if you're using RStudio locally, these are available in the Dropbox folder that was linked earlier. So if you're curious how I got to these pre-processed versions that I'll be using, you can follow this code and perform this code yourself. Instead, I'm going to be skipping ahead to just reading the saved versions of this. So you'll learn more about how to actually do this kind of pre-processing next weekend from Mina in terms of using MS Stats. But I'm just going to go ahead and read in the processed version of this data and get to this IPRG data set. So at this point, what I'm doing is I'm going to use read RDS to load this processed-rpg.rds file. So .rds is one file format that you can use to save R objects. And so read RDS is just reading in this R object that I've already saved from doing this pre-processing up here. And so this is going to give me a processed version of this data set, and I'm going to extract the run level data as a data frame like this. That's what this line is doing. And this IPRG data set, this data frame with 36,321 rows and 13 columns is the version of this data set I'll be using at this point. So what this data is, you have probably heard this yesterday already, but this is a spiked in experiment that had 6 proteins that were spiked in at different ratios in a yeast proteome background. We have, I think, 4 runs that were each reported, or 4 subjects that were each reported, repeated, 3 times in a randomized order. And this data was given to different labs, and the goal was to identify differentially abundant spiked in proteins. So here in this version of the data set that I have at this point, I have columns for run, protein, log intensities, and then a number of other columns for things like subject, group, and other things. What I'm going to do is I'm going to use the transmute function from dplyr to create a simplified version of this data frame. So if you recall, transmute is a combination of select and mutate. So transmute lets me create new columns or new variables, and then also returns a data frame that contains only the columns that I'm creating here. So I'm going to transmute the IPRG data set. I'm going to keep the protein column. I'm going to rename the run column into just run. I'm going to get the log intensities. I'm going to also create a column for the intensities on the original scale. I'm going to do that by just transforming the log intensities that I have. I'm going to get the condition, the subject, and the technical replicate. I'm not going to go into exactly what this function is doing, but this is a function from the string R package. This is another package in the tidyverse that is used for string manipulation. And so what this is doing is, if I look at the original run column here, I can see that the technical replicate identifier is in the last character of these different file names for the different runs. And so what this is doing is this is just doing some string manipulation to extract that last character, so to get whether the technical replicate is A, B, or C. If you're getting any errors, please, either logistics or error questions about errors, please see the TAs for those. I'm not going to be able to go through each individual error, unfortunately. So any questions on the general content or kind of the approach that I'm taking, or questions about Ggplot2, the general code that I'm using, please feel free to ask those questions in the Q&A. for any questions on either logistics, where to find links, where to find the material, or technical questions about I'm getting this error, what should I do about it? For any questions like that or technical help, please ask those either in chat or to the TAs in their Zoom help rooms. So I'm able to answer content questions here. For technical or logistic questions, please direct those to either chat or to the TAs in the Zoom rooms. All right, so if I run this, I'm going to assign this to the IPRG variable, and this gives me a data frame with protein, run, log to intensity, condition, subject, and tech rep. All right, so this is the data frame that I'm going to be using here. So I'm going to go over to the HTML version. All right, so the basics of Ggplot2. Now that I have this example data set that I'm going to be using, let's talk about how some of the basics of Ggplot2. So what we mentioned before in the slides, the components of a plot in Ggplot2 terms. I begin each plot with a default data set and set of aesthetic mappings. Then I can specify one or more layers that each have, at the very least, a geometric object. I always need to specify a geometric object. So whether that's points, which would create a scatter plot, or lines that would create a line chart, I need to specify a geometric object. Then optionally, I can specify a scale for the mapped aesthetics. So things like what specific colors to use, what specific shapes to use. Optionally, I can specify a coordinate system or a facet specification and so forth. So let's talk about how to build up a very basic plot using Ggplot2. So any Ggplot2 plot will begin with a call to the Ggplot function. So I'm going to use this Ggplot function. And the argument I'm going to give to it is just the data set. So here I'm going to specify the argument or the parameter data equals IPRG. So I'm going to specify the data set. And if I just run that on its own without anything else yet, you can see that it actually does create a plot. But all it does is it sets up a blank canvas. So right now I have a blank canvas. That is what is showing up right here. I have a blank canvas with this for this particular data set. Now what I need to do is I should add some kind of aesthetic mappings. So in Ggplot2, that's going to be the second argument to the Ggplot function. After I've specified the data equals IPRG, I'm going to specify the mapping parameter. So this is going to be my aesthetic mappings. And the aesthetic mappings go inside of a special function called AES. AES standing for aesthetics. So inside this aesthetic function, this AES function, I'm going to specify the aesthetic mappings. And so these include things like the X or Y axis for position, color, shape, any kind of aspects of the plot that we want to map to our different variables in our data set. So what I'm going to do is I'm going to map run, the run from this experiment to the X axis. And on the Y axis, I'm going to have the log2 intensities. And so if I just run that, so now if I run that on its own, that will again update the plot that I have. And what it looks like now is I still have a blank canvas essentially, but now I have axes. So on my x-axis, I have the run. I have a bunch of different labels for all of the different runs. I can see they're kind of running together and plotted on top of each other. That's something that we'll fix later on. And on the y-axis, I have log2 intensity and the values for the range of log2 intensity. So I haven't added any geometric objects or marks to draw on the canvas yet. So right now, I still just have a blank canvas. I have grid lines, and I have the X and Y axes marked. So what I can do now is, so I have this call to Ggplot. I have the aesthetic mappings inside my call to AES. And now I can add a geometric object. So I'm going to specifically add the geometric object for a box plot. So this is in Ggplot 2, the way we add geometric objects is through these different geom functions. So there are a bunch of different geom functions. So you can see that there are a bunch of different geometric objects, a bunch of different geom functions dedicated for different kinds of geometric objects and different kinds of plots. Here I'm going to use the one for a box plot. So question, why does log2 intensity start at 18? Is that something that can be specified in the AES function? So here, log2 intensity has the range 16 to 32. The reason for that is if I go and look at the range of log2 intensity in my data set, I can see the range for this variable goes from 16.3 to 31.4. And so since I've given Ggplot my data set and the aesthetic mappings is telling it the variables, it's going to look at those variables, look at the range of those variables, and by default, it's going to create a canvas for the full range of those variables. So since log2 intensity goes from about 16 to 32, I can see my y-axis goes from 16 to 32, and I have labels for each of the different runs in my data set as well. So some things that we'll go over later on is how we can control if I want a different range on my y-axis, or if I want to change these labels so that they're, say, printed vertically instead of horizontally and being all on top of each other. Question, can the keywords data and mapping be omitted? So yes, so in R, whenever we have in a function, when we're calling a function in R, we can always name all of the parameters. And if we omit the names of those parameters, then R will match them based on the ordering. So Ggplot, the Ggplot function, if I open up the help page documentation for the Ggplot function itself, I can see this initializes a new Ggplot object. The first argument is data. The second argument is mapping. And so as long as I have those in that order, I don't need to specify the names. So just for completeness, I showed you with the names of these parameters, but as long as I give them in that order, I do not need to specify those. So here I can run the same code, but without the names of the parameters, and I'll get the same results. So those can be omitted. In general, it's often a good idea to name parameters after the first one. In cases like this, I think it's not as important, but especially when you have a function that has a lot of different parameters. Take, for example, the read CSV function for reading in CSV files. This is a function that has a lot of different parameters. And so when you're using parameters past the first one, in those cases, it's good to name those. But in this case, with just two of these, it's fine to omit them. Yes. All right, so here I have Ggplot, and I'm going to add a geometric object for box plot. And when I add that, I can actually literally use the addition sign to add those two together. So that the way that we build up the different components of a plot using Ggplot 2 is by literally adding them together. So I'm going to have Ggplot. In this call, I have the data set and aesthetic mappings, and I'm going to add geom box plot. And you can see now this gives me a box plot of the log intensity across the different runs in this experiment. And you can find the documentation for all of the different Ggplot2 functions here, as well as look them up in the internal help system in R. So using just the question mark plus the name of a function will give me the help page for that particular function. Using library help equals the name of a package will pull up a documentation page that shows all of the different help pages that are available in that particular package. So these are all the different help pages that I could pull up for the Ggplot2 package. A web version of that documentation is also available at this link. All right, so let's go ahead and figure out how we can build up a slightly more complex plot. So right now, this is how we can build a box plot, just by having our default data set, a set of aesthetic mappings, and adding this box plot. So what we can do now is we can add some additional aesthetics. Suppose maybe, for example, that we want to color these box plots based on question, is the session being recorded, Olga? I don't know if we hit record. I think YouTube
I did not, but it doesn't matter because we live stream and we will just save the live stream version for that service.
Yeah, so we're not recording through Zoom, but YouTube will have a recorded version anyway. So YouTube will have a recorded version, even though we're not currently recording via Zoom. There will be a version on YouTube. OK, so suppose that we want to use the fill color for these different box plots to represent the condition. So I can do that by just adding an additional aesthetic mapping here. So here, I'm going to run this. And now I have a new aesthetic. So I'm using the fill color for these different boxes to represent the different conditions. So I have condition 1, 2, 3, and 4. And I think these are actually just the subjects in this case. So I can add this kind of thing just by setting a new aesthetic mapping. And that's going to remain, I can do that in the exact same way, regardless of what kind of plot I use. So here I'm using box plots, but if I were using, say, if I were doing, say, a scatter plot or a bar plot, if I wanted to change the colors or fill colors and set those to represent a particular variable, I can always just do that inside of this aesthetic mapping. I don't have to figure out how to do that in a different way for each different kind of plot. And that's something that's really nice about the way that Ggplot2 does this. So a question, are the colors set as default? So these are the default colors that, Ggplot2 will have certain colors that it uses by default. We can change these later. I'll show later on how to choose a different set of colors, for example, instead of relying on these. So Ggplot2 will choose a particular set of colors for a default option in all cases. Sometimes they're reasonable, and sometimes there are better choices. In this case, I think these aren't too bad. But if you want to be especially careful about things like being colorblind safe and things like that, we'll talk about that later on in this session, how to set custom colors for those. Question, what is the difference between fill and color? So here, let me try color instead. So there are different aesthetics that can control similar things. So color is one of those examples where there are aesthetics for color and an aesthetic for fill color. So here, if I set just color, what that controls is the outline in this case. So in most cases where we have a geometric object or we're using marks that have kind of an internal part and an external outline, color will be used to control the external part, the outline, and fill is used to control the internal or the fill color. And the same will be true of most other geometric objects that have both an internal part and then an external outline. And so that's something that is especially important, for example, for for bar plots. If I were to make a bar plot, I want to make sure to set the fill color because I'm just changing the outline. That's going to be much harder to see. So that's the difference between fill and color. Fill controls the fill color, so the internal part, and color controls the outline. And in some cases, they'll be the same thing. For example, in a scatter plot, lots of times they'll be they'll be the same thing because many points will just have a single color associated with them. But there can be instances where you would want to control the fill color of a point and the outline of a point separately. But generally speaking, that's the difference between the two. All right, so we've added a fill color here to represent condition, and we can see that also created a legend by default. So this created a legend for me showing the different colors and which condition they represent. Inside of this AES that I use to create the aesthetic mappings, I can actually do inline transformations. So up here, I'm using the log2 intensity. But if I just had the intensity column for the original scale intensities, I can actually do some transformations inside of this AES as well. So here, I'm going to use an inline transformation to make this log2 intensities instead. And I can see that also changes the label on the y-axis here. So I can do inline transformations. So for example, if I wanted to do just the natural log, I could do just the natural log here as well. More commonly, we would want log2, but here, if I do the natural log, I can see that dynamically does a transformation on intensity, and I can see that the y-axis changed according to that because that now has different values for the y-axis. If I change that back to log2, I can see the values change accordingly. Question, when you use fill, the colors that we can see are by default, or you selected the palette before. If you do not specify any kind of color palette, Ggplot 2 will use a default color scheme. So I did not specify these colors myself. These are just the defaults that Ggplot uses. As I said earlier, we'll talk about in a little bit, in a few minutes, how to set these and choose a custom color palette yourself. All right, so because here I did an inline transformation and now have log2 intensity like this, I might not be especially happy with that label now. So I might want to control the axis labels as well as add a title to the plot. So I can do that by just adding an additional component to the plot, again, using the plus sign. So I can use the plus operator and add labs, standing short for labels, lets me add different labels to the plot. So here, inside the labs function, some of the arguments include things like the X or Y axis. I can add. So here, in this labs function, I'm going to add a label for the X axis. I'm going to call it MS run. A label for the Y axis. I'm going to call this log2 intensity. And I'm going to give a title. So I'm going to say this is the distribution of log2 intensity by MS run. If I run all of that, I can see now I have a title in my plot. The y-axis label looks a little bit better, and I've changed the x-axis label as well. Some other things I can control is you can see that by default, Ggplot 2 uses this kind of gray background with these grid lines that show up. But this, along with a lot of other aspects of just kind of how the plot looks, can be controlled using themes. So there are a bunch of different preset themes that we can use. And themes are what we can use to control just different aspects of the plot. I want to say aesthetics, but that should not be confused with the specific, say, X, Y shape color aesthetics. So these are more things like the background color, the default sizes of points, whether a grid shows up or not, things like this, the overall scheme of the plot. So these are some of the themes that are available as presets. And a lot of things are also, you can set kind of custom as well. So what I'm going to do is I'm just going to use one of these presets to show you what it can do. So I'm going to use the theme minimal as an example. And just like I've done so far, as a new component, I can literally just add this using the addition sign. And if I run this, I can see that looks now different than before. This is using the minimal theme. Before, it looked like this. I had this gray background. And now using the minimal theme drops that gray background, so I just have a white background. I still have some faint grid lines there, though. So you can try different themes if you want to find one that is more pleasing to you or is the most interpretable to you. Some other things that you can adjust using the theme are things like the individual text elements for axis labels. So one thing we discussed, I mentioned earlier, was the axis labels for this MS Run labels are very clearly being plotted on top of each other, making them very hard to read. So one of the many things that can be controlled by the theme, if I look at the documentation here for theme, I can see that there are many different things that can be controlled. I'm not going to go into detail about how to control all of these. That's something that you can investigate further later on yourself. But one that I am going to show you how to change is the orientation for those labels, because that's is probably going to be a common issue that many people would need to change. So I want to change the x-axis text labels. So if I go back to help, I can see these are ordered by where they occur kind of in the plot. I'm going to go to look under the axis arguments, axis text, and axis text.x. So this is what I'm going to change because this controls the tick labels along the x-axis. And there are specific functions that I can use to control things like the orientation of text. So the element text function is what I can use to control these different text elements. So here, I'm going to use the theme function to control the x-axis text labels. So I'm going to use the element text function and specify I want to change the angle of these text labels. Some other things you could control are, for example, the font family, the default color, size, and line height, and things like this. I'm going to control the angle. And so if I run this, you can see what I've done here is I've first added theme minimal, and then I've further customized the theme with this additional call to theme. And what this looks like now is I can see everything else looks the same, but I now have, I've changed the orientation for these x-axis labels, so now that they are actually readable. Some additional things that I can change, for example, are trying different geometric objects. So far, I've just been using box plots. Another thing that I could use as to accomplish the same kind of visualization as a box plot is what's called a violin plot. So here I can use geom violin. I just drop that in place of geom box plot. I'm going to keep everything else the same. And so now all that this does now is I have a new geometric object. You can see the violin plot looks very similar to a box plot. The difference is we have now the width of the shapes represents the density or the abundance of observations at that value. So that's why it's called a violin plot, because it'll become wider in the center where there are more data and thinner toward the tails where there's less data points. And so the nice thing about Ggplot 2 is, again, I can just drop in a different geometric object and change the plot, what the plot looks like, but everything else can remain the same. So I'm still using the same data set and aesthetic mappings, same labels and axis things that I've adjusted. And I've just changed the geometric object, and that changes the plot a lot. but everything else remains the same. If I had just, say, a particular function that I had to use to control all of these different things, then it could be quite a bit more difficult, because maybe the way that I control these different things for the violin plot function is different from the way that I can control these different aspects of the plot for the box plot function. Right, so I think now might be a good time to take a break and do some of these first set of exercises. So I'm going to go ahead and let you go off to some of the TA rooms and try to work through some of these early exercises. So if you just open up the HTML document, you can either do that directly through RStudio Cloud, day2exercises.html, or if you've downloaded all the material, just open the day2exercises.html, and you can see I have some questions for you, and you can create most of these just by modifying some of the code that I already have in the RMarkdown document I've been going through. And once you're ready to see a solution, you can click the code button and kind of see what my suggested solution is. And if you need some help, please drop into the TA rooms, and I encourage you to ask them for help and maybe discuss with them your thought process and approach as you're going through these, as well as ask them for maybe more technical questions that I am less able to help you with directly. So I'll take maybe 10, 15 minutes to let you go through some of those exercises, and I'll start talking again. I'll check in again at 1:35 and see if there are some people back or if we need a little bit more time.
But I suggest let's come back at 1:40, so it's 15 minutes, okay, so that people don't kind of worry about that. So let's come back at 1:40 Eastern. And just a reminder, so you need to go to the TA in day 2, right? So November 8th. So make sure you have the link for the second day. And meanwhile, if you want to stay in this main room and work on your own, you can as well. If you have some kind of higher level questions to Kylie, just put them in the Q&A. And otherwise, we will be back at 1:40 Eastern.
Yes. I'll also note a couple of these. Some of the first 2 exercises you should be able to do. The later one, a couple of these other ones might go into a little bit some of the things that we have not quite yet covered, but I at least want to give people a chance to have a little bit of practice with the first 2 exercises here. You can please leave questions for me in the Q&A if you have any sort of high-level Q&A questions. I'll take a look at that. I'm going to quickly run and get some water and and I'll be right back. I'll take a look at the Q&A in just a couple minutes, and we'll be back at 1:45 for continuing with the material.
1:40.
1:40, thank you. Hello, everyone. Checking to see if we need more time with the TAs or if we'll keep going. All right. Looks like we might need a little more time with the TAs for some people, but most people are okay to move on. So what we'll do is we'll move on, but I'm just going to finish up with the first half of the material, and then we will go back and take a break again for TAs for you to give you a chance to complete the rest of the Ggplot 2 exercises. So we will continue with where we left off. So where I am now is we had just added or switched the geometric object from boxplot to geom_violin. And we saw that let us create this violin plot rather than box plots, but everything else, the rest of our code, we could keep the same. All right, so the next thing I'm going to try to do is having multiple layers in our plot. So a common thing we might need to do is have a plot that overlays different kinds of geometric objects. So here, what I'm going to do is suppose I want to, again, have the same kind of plot, run versus log intensities. Oh, I need to switch this back over to RStudio. Sorry about that. All right. So I again have run versus log intensity. I'm going to use fill color for condition. And now suppose I want to have both a scatter plot and a box plot on the same plot. So first, I'm going to add a geom point for the scatter plot. And you'll see I've added a parameter here, position equals jitter. And if I run just these first two lines, here I'm doing that by highlighting them. And you could either click run selected lines, or I hit Command Enter on Mac. I think it's Control Enter on Windows. I could be wrong about the Windows version. So I've added position jitter, and you see what that does is because on the x-axis we have a categorical variable, we don't just want to have a regular scatter plot, because on the x-axis we have a categorical variable run. And so if I didn't add jitter, what this would look like, let me temporarily remove this. This plot would look like this, which is very difficult to read or interpret because all of these points are plotted directly on top of each other. And I can't really tell anything from this about the distribution of log intensity. So that is what geom jitter is giving to us here. This is a position adjustment that adds a small amount of random noise to the x and y values. And this serves to just break the points up a little bit when they're being plotted directly on top of each other like they were in this plot. And so adding a small amount of random noise breaks the points up, but it keeps the overall pattern the same. So if there's an overall pattern or the overall systematic relationships, or the overall distribution, all of these should not be affected by just adding a small amount of random noise, but it just breaks up the points enough so we can actually see what's going on. So I'm adding geom point, and then just after that, I'm going to go ahead and add geom box plot. So I just have a geom point and then a geom box plot, and I'm just adding both of these together along with the rest of what I'm doing here. And now I have a scatter plot with a box plot on top of it. And I did all that just by having geom point plus geom box plot. And this is something that would be much more difficult to do with a kind of a traditional graphic system where I have a function for scatter plots and a function for box plots. This would be something that would be much more difficult. If I run all of this, including my axis labels and my theme. Then I have my rotated x-axis labels and my title and axis labels for run intensity. What I can do now is in this version, so my it's a little bit hard to really, even with the jitter, it's a little bit hard to get an idea of the distribution of log intensity from these points. It makes the whole plot rather dark and ink heavy. So something else that can be useful in a situation like this, what we call overplotting, when so many of these points are being plotted on top of each other, and there's just so much data, is I can set some geom or layer aesthetics. So here I'm going to set the size and alpha value. So alpha represents the transparency or opacity of a layer. And so these are things that are aesthetics, but rather than putting them inside the call to AES, so rather than putting these inside the call to AES as aesthetic mappings, instead I'm just putting them in the call to my geom function, and that's going to be and that's because I'm setting these as a setting for the whole layer, and these are not corresponding to any particular variable. For the whole scatter plot, the whole geom jitter layer, I just want to set the size of the points to be smaller and the alpha level so that these points are very transparent. Another difference I can see is here I had geom point and I set position equals jitter. And here I'm changing geom point with position equals jitter to geom jitter. So a lot of the geom functions in Ggplot2 are actually shortcuts for a combination of geometric object, statistical transformation, and position adjustment. So here geom jitter represents the point geometric object, which we use for scatter plots, combined with the jitter position adjustment. So geom jitter is just a shortcut for geom point, setting the position adjustment to be jitter. And so if I run this, oops, let me try that again. If I run this, I can see now the points are smaller. There's some transparency, so I can see kind of more clearly where the more dense region of points are, and I can have a better idea of the distribution of log2 intensity using the scatter plot that's behind these box plots. Another thing that I might want to do is, so right now I'm using the same color for all of the points here. So the scatter plot part of this plot is all just using black points. So the points here are not kind of inheriting the fill color that I set for the box plots. And that's because for the points, because these don't kind of have an inside internal part to be filled and also an outside outline, these just use the color aesthetic to set the color of the points. So here, because I just have up here, I just had fill color. So the box plot layer is inheriting that fill color, but the point layer is looking for the color aesthetic rather than the fill aesthetic to set the color of the points. So here, what I'm going to do is each layer or each geom function can have its own set of aesthetic mappings that would kind of override the default set of aesthetic mappings. So here I'm going to have my default aesthetic mappings in the call to Ggplot. So in AES here I have x equals run, y equals log2 intensity. I want those aesthetics to be the same for all of my layers for both geom jitter and geom box plot. But then inside geom jitter, I'm going to specify I want a color aesthetic mapped to condition. And in geom box plot, I want the fill aesthetic mapped to condition. And the way this works is that any aesthetic mappings I have in my original Ggplot call, these get inherited by all of the other layers. And then any aesthetic mappings that are only in one of these geom functions is only inherited by that specific layer. So here geom here the color aesthetic is used for geom jitter. The fill aesthetic is used for geom box plot. If I run this, now I can see the points are also using color to correspond to condition, and the box plots are using fill color to represent condition. To kind of build on an earlier question about more about how these differ. So let's take color out of geom jitter, and I'm going to put color back into the aesthetic mapping, the default aesthetic mapping. So I'm going to put it back here up in my original Ggplot call. So what that means now is color is going to be inherited by both of these layers. And think for a moment what is going to change in the plot when I run it this way instead of the way I had it before. So this is when I had color just inside the geom jitter. And now I have color up here. Think about what might change. So if I run this, oops. Oh, I accidentally put this inside the call to log 2. All right, fixing that and running this again. All right, so this is what it looks like if I set this up this way. So now color, so that means the outline color or the point color is being inherited by both layers. So now the points in the box plot are also using the color, and the outlines of the box plot are also using the color for condition. So I end up with a plot that looks like this, as opposed to this one, or this one. So that is what the difference is when I move color up to the original Ggplot call. Okay, and then the last thing I'll mention here is faceting. So if you recall, faceting is when I split up a data into subsets, usually based on the levels of a categorical variable. And then I have subplots that correspond to each of those subsets. So in Ggplot 2, there are 2 ways to specify faceting. One of those is called facet grid. The other one is called facet wrap. These are the 2 functions that we can use to specify faceting. And these 2 functions differ only in the way that they arrange the subplots. So I can actually show you both of these. So here, I'm going to use facet grid, and then I'm going to give it the variable that I want to use for the faceting. So inside of both of these facet grid or facet wrap functions, the way that we specify the variables that we want to use for faceting use what we call this formula interface. So that just means they're going to have a tilde in them, a tilde or a squiggle, or however you call this particular symbol. And so if I run this code, so I've just, like all of the other components, I just add this to the rest of my Ggplot 2 components. So facet grid, so you can see now that this breaks up the data into different subsets for each of the different conditions. And now I have a separate subplot for each of the different conditions. So earlier, my x-axis I had mapped to run. Now here, I'm mapping it instead to tech rep, so the technical replicate, A, B, or C. And my both fill color and faceting, I'm setting to condition. So I have separate subplots for each of these different 4 conditions. And so this is facet grid. You can see it sets up the conditions like this, or the different subplots like this. If I use facet wrap, it instead sets it up like this. So the main difference between facet grid and facet wrap, facet grid tries to set things up. Facet grid is used more often when I'm trying to facet by more than one variable, because it then sets up a grid where along the rows I have the different levels of one categorical variable, or along the rows I have the different levels of one categorical variable, and along the columns I have the different levels of another categorical variable. And that's why when I just use one variable, it sets up the different columns. So I have the different levels of condition. When I use facet wrap, it just kind of takes all of the different possible combinations and plots them in in whatever order they end up appearing. So in this case, that gives me this these 4 conditions in this 2x2 layout. So both facet grid and facet wrap, you can play around with those two and see kind of the differences between them. But what these do, again, split up the data into subsets based on the different levels of, in this case, condition, and then plot those subsets as subplots with the same x and y axes and the same scales as well. So the same, all the same aesthetics, the same colors, shapes, fill color, and so on that we've set apply to all of the different subplots. So now I just have some recipes for some general common plots. So if you think of things like scatter plots, line plots, box plots, all of these things that you might commonly want to make, I'm just going to show you how to make some of these different options using Ggplot 2. So I'm going to start with a scatter plot. So first, I'm going to rearrange the data so that it looks, it's in a format that is more conducive to creating a scatter plot. Because right now, my IPRG data set, I don't really have more than one continuous variable that would be appropriate to plot against each other. I have log2 intensity and intensity, but I'm not going to plot those against each other. Well, I could, but I'm not going to. What I'm going to do instead is I'm going to take my IPRG data set and rearrange it so that I have different columns for each of the different proteins. And I think this is something that should have been discussed yesterday, how to do this. So I'm going to first subset it using select. So I'm going to select 3 columns, protein, run, and intensity. These are going to be the only columns I'm interested in now. And I'm going to use the function pivot wider. I'm not sure whether Ryan used pivot wider or spread. Both pivot wider and spread are functions from the tidyr package. They're part of the tidyverse that are used to accomplish very similar goals. Both of these are used when we have when we want to take the values of a categorical variable and turn these into columns. And these both accomplish the same thing. I'm using pivot wider here because it's the kind of newer version of the spread function. So I'm going to take pivot wider, the names of the new columns. I'm going to, excuse me, I'm actually turning the runs into the columns, not the proteins. I misspoke. Sorry about that. The rows will be the proteins. The columns will be the runs. So the names of the new columns are going to come from the run column, and the values are going to come from the intensity column. So if I run that, the result from that looks like this. So I have a column for protein. So the rows here now just correspond to the protein, and I have columns now for each of the different experimental runs. And what I'm going to do now here, so I'm going to create a scatter plot of 2 of the different runs against each other and just see how they kind of compare for the different proteins. So I'm going to take my Ggplot 2, give it this IPRG2 data set. My X aesthetic is going to be one of the runs. My Y aesthetic is going to be one of the other runs. And if I just use geom point, that will give me a scatter plot here. I've set the a transparency level so that these points are somewhat transparent. If I did not do that, it would look like this, which is not too bad, but there's a little bit of overplotting down near the origin. So that's why I'm turning on some transparency. And another thing that we can do as part of this grammar of graphics is I noticed that it's hard to kind of read this plot because so many of the points are concentrated down here near the origin. That's because I've used the original intensities on the original scale, not the log intensities. And that was so I could show you how to use these scale functions in Ggplot too. So I'll show you more of these scale functions when it comes to controlling color schemes. But there are scale functions that correspond to all of the different aesthetics that you can control in a plot. And so for the X and Y axis, some useful ones are to set these onto a log scale. So I can use scale X and scale Y to change the X and Y axes to a log scale. And that accomplishes essentially the same thing as if I were to just transform the intensities directly. The difference being that the axis labels are on the original scale, and instead just the scaling of the axis has changed. And you can see now putting these on a log scale makes it much easier to read this plot and see the differences between these two runs. Because now the points are spread out across the entirety of my plotting canvas, because now I put these on the log scale. So that's just to show a scatter plot. We can use geom point to create a scatter plot. A line plot, so I'm going to generate some kind of a simulated raw spectrum from my package, Cardinal. There's a function called simulate spectrum there, and this just simulates a raw mass spectrum. So here, MS raw, this is a data frame with a column for the MZ values and a column for intensities. And if I wanted to plot this mass spectrum using Ggplot2, I'm going to give it this MS raw data set. And my aesthetics here, X is going to be the MZ values, Y is going to be the intensities. And I'm going to use geom line because I want to create a line plot to show this mass spectrum. And this particular mass spectrum looks like this. So that's how I can create a line plot using geom line. Box plots, we've already been creating a lot of box plots. The one thing I'm going to show you that's different here is so far we've looked at these box plots like this, and we rotated the axis labels. But another way of accomplishing something similar is to just flip the coordinates. So we talked about Cartesian coordinate systems. You could have polar coordinate systems. Another thing we can do with coordinate systems in Ggplot2 is just flip the axes. So here, chord flip, I can use this to just flip the X and Y axes. So it changes the box plots to the horizontal orientation. And what that also does is that makes it easier to read these labels without using the theme function to rotate them. Instead, here I can just flip the axes. So that's another useful little thing that I can do with the coordinates in Ggplot2. Histograms. So here, I can use geom histogram to create a histogram. So I'm going to look at the distribution of the log intensities. And if I just do that using geom histogram, I can see the distribution of log intensities looks like this. Looks reasonably symmetric, kind of normal with this log transformation. Another thing I can do is suppose I want to look at the distribution of the intensities for each individual run, but as histograms rather than box plots. I can do that using faceting. So here I'm going to use facet wrap on run, and that creates a subplot for each individual run now. And so I can see a different histogram for each run. This is another example where, let's say, I'm going to use the intensities on the original scale. So if I, instead of log to intensity, if I just use intensity, well, I can see the log transformation helped a lot because otherwise these intensities would be very skewed, Here's another example where instead of directly transforming the variable, I can change the scale of the x-axis. So here I'm going to use scale x log 10 to instead scale the axis itself. And again, I can see this accomplishes a similar thing to transforming the variable itself. Bar plots. there wasn't much to be done in terms of bar plots here. So I'm going to use the, which I never actually loaded earlier, but I'm going to go back up here and read in this IPRG data from the CSV file. I believe this is what Ryan was using yesterday. So this is just the IPRG 2015 Skyline CSV data in this data frame called raw. And here I'm just going to create a bar plot from this to show you how to use geom bar to make a bar plot. And here I'm just looking at the counts of product charge in this data set. Right, so that's just a quick run through of some of the common statistical plots that you might want to make in Ggplot2 and the geom function that corresponds to each of them. So what I want to talk about now is color palettes. So I got several questions on color palettes earlier, and that is a very important thing to consider when creating visualizations and plots. So a very useful package for working with color palettes, especially categorical color palettes in R, is the Color Brewer package. I believe this comes automatically with the tidyverse. It's not part of it, but Ggplot2 relies on it in some ways. So I'm going to display all of the possible color palettes included in this Color Brewer package. I'm going to switch over back to, oh, actually, I don't need to do that. I'm going to switch over to my HTML version here, since I have a little more room to display that here. So these are a bunch of different color palettes that are available in the R Color Brewer package. And these come from the colorbrewer2.org website. And this is a very useful website that was put together by some data viz people from it looks like the Pennsylvania State University. These were hand-picked color palettes put together by some very smart color viz people. And you have different kinds of color palettes that you can choose depending on what kind of data you want to represent. And you can specify certain things like you want only colorblind safe palettes, you want print-friendly palettes. So these are 3 colorblind safe palettes for qualitative or categorical data. You might want ones that are good for print or things that are good for photocopying and so forth. So this can help you select a choice of different color palettes that are useful for whatever you want to represent. And our Color Brewer is the R package that goes along and with this website and provides all of these in R. So let's talk about the different kinds of color palettes that you have available. So the first thing are qualitative color palettes. So these are for representing qualitative or categorical data. So these are when you have a categorical variable and you want to represent the different categories here. So what's important when choosing a qualitative palette is that each of the different colors should be easily distinguishable from each other. Another thing to consider is that you don't really want to show too many categories using color, because past, I want to say, 6, 7, 8 colors or so, we have a really difficult time distinguishing colors past 6 to 8 colors or so. So in the colorbrewer.org website, I can select the qualitative color palette. So these are different color palettes I can choose for categorical variables. If I want to look for colorblind safe palettes, for 3 classes. I can see the candidates here are dark 2, paired, so the name shows up here, dark 2, paired, and set 2. If I look up to, say, 6 classes, none of those are colorblind safe actually for 6 classes. But if I turn that off, I get a number of different options. Let's try 5. So you can see that if you want to be colorblind safe, you really can't even go past 4 classes. Unfortunately, that isn't practical in a lot of instances. So I'm going to just look at these. So dark 2. So here's an example of a palette that I might want to use. So if I want to use this palette in Ggplot 2, I can set a scale for this. So here, I'm going to run these first several lines. So you can see, so this is my box plot that I've been using so far, looking at distribution of intensity by MS run. And suppose I want to set a custom color palette for condition here. So this is just the default one that Ggplot selects automatically, but it's not going to be ideal, especially if I have a larger number of colors or categories. So what I can do to choose one custom from this color brewer website or package is I can set scale fill, because I'm choosing a fill color. If I were setting the color aesthetic, I would choose scale underscore color brewer instead. So scale underscore fill to set the fill aesthetic scale. And then brewer lets me choose from the different possibilities using the color brewer website. So I can use the palette parameter to specify the name of the color palette that I want to choose. So I'm going to choose dark 2. And now if I run that, I can see that now uses the color palette for dark 2 from the color brewer website. So that's a qualitative palette for continuous variables. For when it comes to continuous palettes for continuous variables, there's 2 different kinds that I want to talk about. Just to better show these, I'm going to use a data set that lets me kind of show these more easily. This is not a mass spec data set. This is a volcano data set of an actual volcano. I need to spell volcano correctly. From Auckland's Mangawau volcano, English name Mount Eden or Mangawau. It's one of 50 volcanoes in the Auckland volcanic field. And so I'm just, by default, this comes as a matrix. I'm going to reformat it here into a data frame so I can plug it into Ggplot 2. I'm not going to explain what this code does right now. You can ask a TA because I just want to move on to showing how to use the color palettes. So I have Volcano 2. This is my data frame representation of this volcano data set. And in terms of color palettes for continuous variables, first let me show the kind of default. So I'm going to set my aesthetics X for the X variable, Y for Y, fill color for the Z, and then geom tile is the geometric object that Ggplot 2 uses for things like heat maps or images. So this is the volcano. It's a topographic map that you can kind of see. So here you can see the lighter part is the volcano as it goes up higher in elevation. And this is the default color palette that Ggplot 2 uses for continuous variables. And you can see another use of a setting manual coordinates. Here I'm going to use chord fixed. And what that does is it sets it so that by default, if I change, say, the size of the palette, the X and Y axes stretch. And so instead, what I'm going to do is if I set chord fixed, it changes it so that the X and Y axes stay fixed no matter the size of the canvas, which is something reasonable to do with either image data or, in this case, topographic data. So if I want to set a custom color palette, I can use scale fill again. And for the color brewer palettes, Ggplot 2 uses the distiller, calls these distiller for the continuous palettes. So brewer for the qualitative ones and distiller for the continuous ones. So here I'm going to set a continuous color scale, and I'm going to choose a sequential color scale. So this is useful in this case when I have kind of a sequential color scale from, in this case, say 100 to 190 or whatever this is. From the Color Brewer website, these are the sequential scales. So this is when there's, when I don't really have necessarily a center point that I'm orienting around. The two kinds of continuous color scales are sequential or diverging. Diverging is what we would use when we have kind of a central point that we're orienting around. So this would be, for example, if you have, if you want to represent, say, probabilities, and you want to represent, say, in the middle is a 50-50 probability, and on either side is maybe the probability of healthy and disease. And that's kind of oriented around a 50% probability in the middle. Versus sequential is when we don't really have a center necessarily. So I'm going to choose the blues color palette from our Color Brewer, and that looks like this. So I can choose these different color palettes here for the sequential. If I wanted to choose a diverging one, let's say this purple-green one. So I'm still looking at colorblind safe ones. So this purple-green one is if I wanted a diverging color palette. So this is PRGN. So back over to here, I'm going to choose this diverging color palette. I'm going to choose scale fill distiller palette equals PRNG. And so what I've done to slightly modify the data so it's more appropriate for a divergent scale is I'm just standardizing the Z dimension here so it's centered around 0. But that's how I can choose a custom continuous color palettes and custom categorical color palettes using these Color Brewer palettes that are very useful, especially if you want to make sure things are colorblind safe or print friendly and that kind of thing.
Kylie, there's a question. Could you repost the link to the Grammar of Graphics? There was a question in the chat. I think the poster referred to the color choices that you were showing.
OK, I'm just going to post several things. So here's all of the material that includes the slides. And I'm going to post here. Let me post the link to this Color Brewer website. So here's colorbrewer2.org. That's for choosing color palettes. And again, these are just a number of hand-picked color palettes that you can choose to be known either colorblind safe, print friendly, and so forth. One other one that I just want to mention that's included with Ggplot 2 that is also useful, especially for continuous color palettes, is the Viridis family of color palettes. So this is another set of color palettes primarily for continuous color palettes. Viridis, this is, I think Ggplot actually uses this now as the new default for certain color scales, not all of them, but this is another useful one that has various colorblind safe versions of it as well. All right, so the last thing I want to go over before I let you split off into TAs again and work on some of these exercises is just how to actually export plots and figures from R, because that's something very useful to know. So if you are using RStudio, one way you could go about doing this is just click on this nifty export button in the plot section and save as image or save as PDF. but that's not super reproducible. So I'm going to show you the kind of most preferred reproducible programmatic way to export these plots. If you're just kind of experimenting and want to save something quickly, this export button is helpful if you're using RStudio. But if you're really preparing things for publication and want to make sure that it's easy to reproduce your plots, it's much better to do it this way that I'm going to show you. So first, I want to show you how to kind of store Ggplot to graphics in an object or in a variable in R. So far, we've just been displaying the plots as soon as we create them. But we don't have to do that. So here, we can actually save or store these Ggplot2 objects in a variable. So here, Ggplot2, if I just run this, what it does is it sets up this canvas for the data set and aesthetic mapping I've given it. But what I could do is I can assign this to a variable. I'm going to call it G. And so G now stores essentially the output of this call. It's going to store a Ggplot object. And what I can do now is I can just use G as a stand-in for what I've done here. And now I can use G. I can add, say, a layered geom jitter. So if I take G plus geom jitter, color equals condition, I can get this. And say now I can take G plus geom jitter plus geom box plot. This gives me this kind of plot. And I can assign this as a variable again now as, say, G2. So the way that Ggplot2 works is when I do this assignment, nothing's going to get plotted. But anytime I take one of these variables and just type it and hit enter, it's going to get printed out. And what that means for a graphic is it's going to get plotted. So here, this is G. You remember, G is just this original call to Ggplot. G2, this is this box plot with the scatter plot overlaid behind it. And so now, and this is a really useful thing if you have, say, a very complex plot and you want to store part of it, or maybe you want to try modifying small parts of a plot, or you have a series of plots that's just going to be changing small things between them. You can store the common part that all of those plots are going to use in a variable, and then just change the part, the small parts that you're going to change in that series of plots. So this is a nice thing to take advantage of, that you can store Ggplot2 plots in a variable. All right, so how to actually export these. So R displays plots using what are called, using graphics devices. There's a bunch of functions that I'm not going to go through all of them for controlling graphics devices in R. One of those is just dev.list. Most of these are prefixed with dev for device. So dev.list just lists the current graphics devices that RStudio is using. So here, if I look at this, I can see that I have two current graphics devices, RStudio graphics device and one for PNG. And I can find out what the current one is. The current one being used is the RStudio graphics device. I think there's a second one for PNG here, because the way RStudio is working is it's first creating a PNG and then loading that into the RStudio graphics device to show here. But dev.list shows the different graphics devices. I can get the current one like so. But what I can do in order to export any plot from R, applies to any plot, not just Ggplot2 plots, any plot, is to create a new external graphics device for a particular file. So there are different functions for this that correspond to different file formats that you might want to export to. So PDF, PNG, and so forth for different either PDF or different image formats. So there's a question that I missed earlier. Can these earlier color palettes, so the ones I showed up here, be applied to hierarchical clustering plots? So these specific ones that I showed you, so this is something that we might not have time to cover. We'll see how much time we have for this, for the rest of the material, but we are quickly running out of time. But if you want, you do of course have access to the rest of the material that I have for working with a bunch of different kinds of specific kinds of plots, and one of those is hierarchical clustering. And because a lot of the kind of specific plots for working with certain kinds of analyses, unfortunately, we're not always able to work with those using Ggplot 2, because a lot of these are programmed using different graphics packages, depending on who wrote the original function for doing that kind of analysis. So the ways for controlling certain things like colors and hierarchical clustering can vary depending on the specific function used to plot those objects, the results of those specific kinds of analyses. And so unfortunately, we can't control those directly in the same way using the same functions that we can in Ggplot 2. But if you look ahead to day 2b, and this material, I do show you some examples of how to control certain labels in hierarchical clustering. And if you wanted to apply these same color palettes, so the ones from the Color Brewer website, you would use the rcolor brewer functions directly. So in our color brewer, there's a function called colorbrewer.pal, and you would here specify, say, the number of colors that you want. Let me need to actually load our color brewer. You would specify, say, the number of colors and then the palette that you're using. And you could plug these directly into whatever plotting function is used for the particular kind of analysis that you're displaying. All right. So back to exporting figures. So here we can create an external graphics device. I'm going to show using a PDF. Oops. So I can use the PDF function to create an external PDF graphics device. You can specify things like the height and width of the canvas, as well as other things like the file name. So I'm going to call it test-figure.pdf. There's a number of other things that you can set here. So if I just run this line to create this PDF, you can see that that creates a PDF file. Right now, there's nothing in it, but I could see if I list the graphics devices, there's now a new device called PDF. And if I check the current device is now PDF. And so what happens is whatever plot that I create, let me run this code, for example, to create this plot that has the box plots that I was plotting before. Any plot that I create now will actually be plotted in the file. So this is being plotted in the PDF file that I just created. That's why no plot showed up when I ran that code just now, because it's in this PDF file. Now, importantly, once I'm done with this, I need to actually close the file and turn off that graphics device. So I've done my plotting, and I need to use dev.off to turn off that graphics device. And now it turns off that PDF device, and my current device is now reset to the RStudio graphics device. And so now, if I wanted to go look at test-figure.pdf, if I open that up, I can see it is that plot that I created and exported to that PDF file. So you can use these different functions to create different kinds of external devices for PDF, PNG, TIFF, JPEG, and so forth. And then any plots you plot will be sent to that file that you create. And then at the end, you want to call dev.off to turn off that device and close the file before you access it. And then you should have a plot in a file that you can use for publication. There's a question, is there a way to remove the gray lines in the plot? Is it possible to export TIFF with 300? OK, first answer the grid lines. So so remember things like the background color, grid lines. These are all things that using Ggplot2 we can control through the use of themes. And so here I have grid lines in theme minimal. Not sure which one of these does not have grid lines. Let me check. Theme classic does not have grid lines. Thank you, Emily. So theme classic is an example of a theme that does not have grid lines. So here, theme classic looks very reminiscent of base graphics in R. So here we just have the axes and no grid lines. Theme classic is one of the themes that does this. You can also create your own custom theme. I don't remember exactly which parameter you set to control whether there's grid lines or not. But this is one example of a theme that does not include them. So this is all controlled through themes in Ggplot2. Is it possible to export TIFF with a certain DPI? Yes. So for any of these functions, you can look up the documentation and see the different things that you can control. One of these is, for instance, height, width. I think the point, I'm not sure. Res here, I guess. I think this is what you would want to set in this case. So you can explore the documentation and the different parameters you can control for the different image formats that you can have here, but you can control a bunch of different parameters like the DPI, the height and width and pixels and so forth. OK, so as a final note, I want to mention the session info. So whenever you're doing work in R, it's a good thing to print out the session info for people who might want to reproduce your results. So I'm currently using R 4.0.3. These are the packages that I have loaded if you want to reproduce what I've been doing so far. So I do have another set of material which we may or may not get to, as I said, but before if we even try to attempt any of that, I want to give you a chance to go back to the TAs and complete any of the exercises from Ggplot2 that you may not have gotten a chance to complete, since some of these do use some things that we just went over recently. So go ahead, especially for the people who wanted more time with the TAs, give you a chance to have some more hands-on with them and complete the rest of the exercises. And for anyone who is a bit more advanced and maybe has already done those, you can maybe look ahead to the next set of material and try to do some of the exercises from there.
So what time should we come back? It's 2:35.
Let's say maybe 2:50.
Sounds good. And we will have another 25 minutes after that.
All right.
So 2:50.
Let's see. We do have a question. Can a graph be created with a zoom-in region of a part of the axis? Let's see. OK, so I think what you mean is you have a plot, and then on top of that, you want to overlay another plot. Yeah, so There's some using just pure Ggplot2. I'm not sure if there's a way to do this. There are a number of packages that kind of extend Ggplot2 and let you do kind of things like that, like take a Ggplot2 graph and then on top of it add another Ggplot2 graph. I think Grid Extra is the name of one of the packages that does things like that. There's another one called Patchwork, I think. So Grid Extra is one of the packages that you can just create a Ggplot2 plot and then kind of do things like overlay one on top of the other and things like that. Specifically for that kind of thing where you have a plot and then you want to overlay another one on top of it, what I actually do is, personally, I would prepare those two plots separately because I think I think there's not necessarily a need to have that layout be controlled programmatically. What's important is that the content, the data content of the plot is reproducible. So what I might do instead, you can, I'm sure, do that using a package like Grid Extra to control that programmatically. But what I would probably personally do is I would prepare two separate plots, the larger region and then the zoomed in region. And I would just create, kind of customize it myself using something like PowerPoint or Keynote or Illustrator or something like that to prepare the final graphic. I think that's something that we haven't really talked about, but I think it's useful to create all of the data content and what needs to be reproducible using something like Ggplot2, but then certain things that maybe don't need to be as reproducible. So maybe setting further customizing access labels or things like that, or doing something more advanced like layering completely separate plots on top of each other or arranging them in certain ways. For that kind of thing, you can sometimes use a drag and drop thing like Adobe Illustrator or even just PowerPoint to do that. So you can use a package like Grid Extra to do that. You could also just prepare them separately and prepare them using another application, which is actually what I tend to do in practice for that specific case.
So I see quite a few people still staying in the main room. So I just want to once again encourage you to find your TAs because they can help you with the questions.
Hello again. I'm going to check in again with the people who are here and see if anyone wants more time with the TAs.
If you are just joining us, please respond to the poll if you haven't done already. It looks like it was okay, but probably those who need more time with the TAs, they're still with the TAs and they can't respond to the poll.
Yes. All right, so what we'll do is we'll keep going, but the remainder, we don't really have enough time to go through the remainder of the material in more detail. So you have the RMarkdown document for statistical graphics for MS. So this is day 2B dash either .rmd or .html. What I will do is, because we don't have much time left, I'm just going to go through the HTML version of this and kind of give you a general overview of kind of the landscape of some analyses that are common for MS data, as well as where to how to approach the visualization for some of these. The difficulty is that a lot of the specialized packages for doing some of these kinds of analyses don't actually use Ggplot2. So Ggplot2 is great when we have access to the data itself, when we have a tidy data frame that we can use and build really great visualizations using Ggplot2. But that's not always what we are able to do, especially when we have, say, hierarchical clustering or PCA results, or want to do a heat map. Some of these are going to be easier to do either using other functions, or we have to build, or we just have to use the functions that the package authors give us for working with their particular kind of analysis results object. So I'm just going to go through some of these different analyses that you might do and kind of where to find or how to do some of the basic visualization for these things. So again, we have the IPRG data set. For some of these, I'm also going to actually need a different data set. Again, I'm not going to go through and run some of these. I just want to give a general overview since we are short on time. Between today and next weekend, you can kind of look through all of this code and run it yourself as kind of homework. You have examples B1 through, or exercises B1 through B5 that correspond to this material that you can do at home over the next week if you have time, or if you're curious and want to get some more practice with some of these things. All of the solutions are available again for the exercises. They're in the RMarkdown code, and if you're just looking at the HTML, you have the question, and clicking the code will show you this, at least my solution. So I'm also going to use a CRC training data set. So this is a training data set for detecting colorectal cancer. This is from the MS Stats biodata package. So this is a package on bioconductor that has some data for the MS Stats package. And this is training data that has 100 subjects in the control group without cancer and 100 subjects with colorectal cancer. And again, there's some pre-processing that is associated with this that I'm not going to do or go through, because next weekend you'll get more on how to actually use MS Stats. What we just need is the output data, which is a matrix of quantification information for all of the different patients and all of the different proteins. So this is just the first 5 rows and columns of that matrix. So although we've been using Ggplot 2, which I think is the best way of going about creating custom graphics and creating statistical plots in R, for some of these other kind of analysis packages that we use to get results, sometimes they don't use Ggplot 2 and sometimes they use base graphics in R. And so I just want to give you kind of a brief background of base graphics in R, so you're at least somewhat familiar with how it works in case you're using a package that relies on using base graphics. So base graphics in R uses what we call a brush on canvas approach. So you start with a blank canvas and then you one by one add elements to it. So you add lines, you add points, or things like that. So here I'm creating a scatter plot using the plot function. I'm specifying that these points are blue. Here I can add a line on top of that and add a particular, say in this case, a vertical line on top of that as well. So it's a bit of a different approach. We have specific functions for creating specific kinds of plots. But one important thing if you want to customize plots from some of these other packages that do rely on base graphics is kind of the translation between the Ggplot 2 aesthetics and the terms for some of these things in base R graphics, which in some cases are a little bit weird. So in Ggplot 2, we have color and fill color. And in Ggplot 2, these are different things. So color usually refers to the outline color or the color of points. Fill color usually refers to the internal fill color of shapes. In base graphics, both of these are just called col, short for color. In Ggplot 2, we have shape. This corresponds to the shape of points. In base R, this is the slightly weird parameter PCH controls the shape of points. Size for points or text labels in Ggplot 2. In base R, CEX, again, a slightly weird naming scheme. CEX controls the size of graphical elements. So again, this is just a kind of a strange thing. Size for lines specifically in base R is LWD. That's short for line width. And line type in Ggplot 2, in base R, it is abbreviated LTY for line type. So these are just things if you're using a base R plotting function, these are the parameters you would use to control some of these different plotting aesthetics. And especially if you want to customize a plot that is produced by a plotting function from a particular package that does not use Ggplot 2, that uses base graphics instead. So as an example of some of these base graphics, here is a scatter plot just using the plot function. Here's a line plot using the plot function, but the type parameter is used to say that this is a line plot instead. Here's a box plot using the box plot function. Here's a histogram using the hist function. And here's a bar plot using the bar plot function. And in some of these cases, these look simpler in some cases than the way we would make these in Ggplot 2, but it's quite a bit harder to actually customize these plots. which is the major drawback of having these kind of dedicated functions and having this kind of base R approach. In Ggplot 2, it is much easier to customize plots and make these big kind of adjustments of setting, say, fill color and faceting and all of these other really powerful ways that we can control these different plotting aspects. These are much harder to do with base graphics. All right, so suppose you want to cluster data. This is a common thing. There was a question earlier about hierarchical clustering. So clustering is a way, common way to explore unlabeled data, especially for visualization. And the idea behind clustering is we want to find subgroups that are relatively homogeneous within the data. So we want to group together different points based on their similarity. For clustering, we typically need the data in a numeric matrix rather than a data frame. So that this CRC data that I pre-processed up here, again, I'm not going to go through the pre-processing now, but the end result was a numeric matrix where the rows are the patients or the subjects or samples. The columns are the proteins. Note that this is another kind of difference between some of these analysis functions. So commonly in bioinformatics, in mass spectrometry, and the different omics, whether it's proteomics or lipidomics, metabolomics, genomics, oftentimes when we have data as a matrix, we use the rows as the proteins or the genes, and the columns are the samples or the subjects. For a lot of these analytic functions, for example, clustering or PCA, things like this, they expect it the other way around. So here the rows are the samples and the columns are the proteins, for example. So this is the CRC data, the colorectal cancer data. For some of these, I'm also going to use a simpler data set. This is a data set that comes with R. And that's just because this CRC data is real, so it's very messy. This iris data is measurements on flowers. It's also real, but it's a lot neater and smaller and simpler. So it's kind of a little bit easier to understand the results in some cases, whereas the CRC data is rather noisy and not very well behaved. So this is a small amount of pre-processing that was done on this iris data to put it into a matrix as well. All right, so hierarchical clustering. So this is when we either start in a bottom-up approach where each data point begins as its own cluster, and we want to merge these until ultimately there's only a single cluster. Alternatively, we could use a top-down approach where the data set begins in a single cluster and we iteratively split these up until each data point is its own cluster. There are different kinds of dissimilarity measures we can use. So we can use the actual Euclidean distance between points. We could use correlation if we want to use more of a correlation measure rather than the actual difference. And there's also different ways that we can define dissimilarity between clusters as a whole. So once measuring dissimilarity between two individual points is straightforward and easy. We just either use, say, the correlation or the actual distance. But once we have clusters and we want to decide whether to join a cluster or keep it separate, then we need to decide how to define dissimilarity between groups or clusters of points. And there are different ways of doing this. Complete linkage refers to, we're just going to take the maximum distance between all of the different points in these clusters. Single linkage means we're just going to take the minimum distance between these different points. Average just means we're going to take the average of the differences between the sets of points in the cluster. So these are just kind of different options that you can try, and these will result in different clustering configurations. Here's an example of using complete linkage. I'm going to do hierarchical clustering on this CRC data. In base R comes with a hierarchical clustering function called hclust. This is applied on a matrix of dissimilarity measures. Dist is a function that just creates a Euclidean distance matrix. And if I just plot this, it uses the base R plotting system, and I get this dendrogram of, at the top, we have all of the data splitting into 2 clusters, and then down here at the very end, each individual data point is a separate cluster. Unfortunately, it's hard to read the data labels in this case, but this data, this CRC data, did not cluster very well. The healthy points and the cancer points are kind of all mixed up with each other. We got a question earlier on how to get colors into these dendrograms. I'm using the dend-extend package to do this. So this dend-extend package is really useful if you want to customize dendrograms when you're plotting results from hierarchical clustering. I highly recommend taking a look at this. Otherwise, it's very hard to control some of these plots. And so here I'm assigning label colors based on the actual label. And so now you can kind of more easily see that these healthy and cancer patients are all kind of mixed together. So unfortunately, this data didn't cluster very well. Here I'm just plotting the first 2 proteins, the intensities against each other. I'm using the color to represent the first 2 clusters. So when you're doing hierarchical clustering, you can use a cut tree to decide you want to cut this dendrogram at a certain point. I'm cutting it where there's 2 clusters here. And I'm using the shape of the points to represent diagnosis. Again, this is just another way of seeing. Doesn't look like this data clusters very well, unfortunately. The iris data cluster is quite better. So here you can see we have 3 different species of flowers. And this is just an example of data that clusters much better in this case. And again, I'm using the dend-extend package here to label the colors of this dendrogram for the labels. K-means is another method of clustering. I'm not going to go through the details of how K-means works, but this is a method of clustering where you have to decide on the number of clusters beforehand. I'm going to just set this to 2. And what this does is this goes through an iterative process and tries to find clusters such that if we take the mean of all of the data points in the cluster, each data point is assigned to the cluster with the nearest mean. And again, this data does not cluster super well. Here's an example of the iris data, which clusters a little bit better. Again, just for time, I'm going to briefly mention dimension reduction, since some know PCA is a common method that people ask about. So PCA is a classic dimension reduction method where we want to kind of decompose data that has a lot of variables and represent all of those variables with just a small number of variables that are some kind of linear combination of the original data. So PCA has a nice aspect of it. It produces orthogonal dimensions. So the principal components are uncorrelated with each other, which is very useful for things. And so in base R, you can just use PRComp to get a principal components analysis. If I call summary on this, it'll show me the proportion of variance explained by each of the individual PC components and the cumulative variation explained. Ideally, we'd like to have just a small number of principal components that explain, say, 70, 80% of the variation in the data. It looks like it takes about 7 components before we can explain that much amount of variation in the data. If I plot that, I can see what the kind of the first few components will explain as much variation as possible, and each component after that does not explain as much. So question, is it easy to complete correlated PLSDA and visualize VIP scores? So PLS is another dimension reduction technique. PCA and what I'll be talking about in a moment, TSNE, PCA and TSNE are what we call unsupervised dimension reduction techniques. So they do not rely on data labels. PLS is a dimension reduction technique that is supervised. So it does rely on either data labels or a response variable. So PLS is often used in the context of either regression or discriminant analysis. And so there are a number of packages for using PLS in R. I don't remember the names of them off the top of my head, unfortunately. So it's not one of the methods that's built into base R. So there are some packages on both CRAN and Bioconductor have packages for using PLS. So I'd have to look into one of those packages. There are several options for that. I don't have them as part of this material right now, so you would have to, you should Google those, or maybe one of the TAs can point you to an option for that. So PCA, I can use this byplot function. This creates just a simple plot of the PC loadings against each other. So plotting the weights that are used shows kind of, actually it looks like this is both the loadings and the scores. This is a little bit of a confusing plot. So it's better to, I think, look at the PC scores directly. So if I extract the X component of the results here, this is the matrix of the scores. So this is what I would plug in if I wanted to do, say, linear regression on this or something. And here I'm just going to plot the first two principal components against each other, and I'm going to fill in color. So remember, in base R, col is the color using the diagnosis. And unfortunately, I can see what I would hope is, looking at these first two principal components, I would hope to see some separation between healthy and cancer. Unfortunately, I don't really see that here, so this data does not appear to separate very well. Iris data, I can see I've done the exact same thing here. Coloring based on species, I can see this data. Looking at the first two principal components here, it looks like it separates much better. TSNE, I'm not going to, again, go into the details here because we're close to running out of time. But TSNE is a kind of a more complex, stochastic, nonlinear dimension reduction method. It requires some parameters that you need to set, and it often takes quite a bit more time to calculate than PCA, but it can sometimes better capture separations in the data when it's when those separations are nonlinear. So unfortunately for this CRC data, again, we don't really see much separation. For the iris data, we do. And this was using the RTSNE package. So this is a package you can use for TSNE dimension reduction. Heat maps, a common thing to want to do. In base R, there's just a function heat map that will create a heat map for you. We saw in Ggplot 2, you can use the geom tile function to create essentially a heat map. What the base R heat map function will do that is much more difficult to do in Ggplot, unfortunately, is have these dendrograms on either side of the heat map. So this is hierarchical clustering that has been done prior to displaying the heat map to rearrange the samples and proteins in an order such that the most similar ones are closer to each other in the heat map. So that is one thing that is done using the base R heat map that is a bit harder to do using Ggplot 2. I'm going to skip over visualizing P distributions with volcano plots. This is very important, and I know lots of people would have questions about this, but this is something that I believe Mina will also cover when discussing statistical analysis using MS Stats. So you'll see more about volcano plots and visualizing p-values more next weekend with Mina, since you'll be doing a lot more statistical analysis then. So the last thing I want to show before we're out of time is intersections. So a common thing that you might want to do is maybe find out which are the common proteins that you found between different kinds of analyses. One way of doing that might be to do Venn diagrams. So there is, you can do Venn diagrams using a couple of different packages. Ggplots, not to be confused with Ggplot2. Ggplots is one package that you can use to create Venn diagrams. So here, I'm just using the Venn function to create these Venn diagrams here. And here I'm finding what are the common and different proteins between different contrasts in the IPRG data set. And so this is done by first creating a list that has a list of which proteins are in which were found significant in different contrasts, and then giving that to this Venn diagram, Venn function for Gplots. So this is a very nice function in a very useful package, but these are fairly basic Venn diagrams. The Euler package, Euler R package, has some more kind of prettier Venn diagrams. And so if you really want some kind of more advanced Venn diagrams that might look a little bit better, I really recommend the Euler package. This is a little bit more complicated to use, but gives you a lot more control over the Venn diagrams that you can create with this. A common problem with Venn diagrams, though, is if you have really more than two sets, Venn diagrams are really difficult to interpret and create and read when you have more than two sets. And so the last thing I want to show before we're out of time is upset plots. And so these are an alternative to Venn diagrams for looking at intersections that are especially useful for when you have more than two sets that you want to compare. So from that IPRG data set, I think I had a total of, there's a total of 6 contrasts. So if I just look up here, Mina will go over how to set these kinds of things up. So there's 6 different comparisons between different conditions that we did that were fit here. So 6 different contrasts that are being made. And if I want to look at the common proteins that are the same and different between all 6 of those different contrasts, it's really hard to do that using a Venn diagram. The upset R package lets you create what are called upset diagrams. And here along here we see the different sets. We have a bar plot showing the intersection size, and then showing here with these filled in circles and kind of links between them shows the number of points that are common between all of these different sets. So we had the way we would interpret this is we had 2 proteins that were found in common to be statistically significant between 5 of these contrasts. There was one contrast that didn't find anything, so that's why in this result, there's only 5 that actually show up. So 2 proteins that were found by all 5 of these, 1 protein by just contrast 2-1, and 1 for each of these other combinations of different contrasts. And you can change the ordering that these are displayed in, and set up and look it up and only look at particular subsets. But in general, these upset diagrams are an easier way to look at these kinds of intersections when you have more than 2 sets. So I highly recommend them. There's a website dedicated to creating these upset diagrams. I think Nils Gellenborg is one of the people that came up with these. And these are very useful for visualizing this kind of data. Finally, we're at time. We were not able to go through this second set of material in more detail, but you have access to all of it on Dropbox. So I encourage you to run the R code here and complete the exercises on your own time. You have all of the solutions in the RMarkdown documents for these exercises. So I hope you're able to do that, and I hope the material on Ggplot2 was helpful. And thank you.
Well, thank you very much, Kylie. So I think that concludes our time for today. So we will be back next Saturday again at noon Eastern, where we will be talking more about using R in the context of statistical analysis. So indeed, thank you, Kylie, for bringing this slide up. So we have a large group of teaching assistants. I hope that this was helpful for you. In fact, we would like to hear from you regarding the experience this week and if there's anything we could change for the next week. So we will be sending you a short form very shortly, if you don't mind answering questions, because it gives us 5 days to make some changes if necessary. And we're very grateful to all the teaching assistants who give their time during the weekend for that. So we will stay on for a few more minutes in case you have questions to Kylie or to the TAs. If not, thank you very much. And we will see you again next Saturday. I hope that this was useful.
Yes. Thank you, Olga. And thank you so much to Olga, Mina, and Ryan for setting so much of this up. And thank you to all of the teaching assistants who really made this possible. I certainly couldn't have done this without all the people available to help with kind of more personalized problems. So thank you to everyone. And I hope everyone was able to find some of this useful and is able to rejoin us next week for Mina and Olga talking more about some statistical analysis.